Welcome to this comprehensive lecture on scaling laws across multiple scientific disciplines. Today we're going to explore one of the most profound principles in science, how properties change when we scale systems up or down in size. Let's start with the fundamental question. What exactly are scaling laws? Scaling laws describe mathematical relationships that tell us how various properties of a system change when we change its size or scale. Here's the key insight. Not everything scales linearly. When you double the size of something, some properties double, but others might increase by a factor of 4, 8, or even more. The most fundamental scaling law is called the square-cube law. This law governs everything from why insects can lift many times their body weight to why there's a limit to how tall buildings can be. When you scale an object by a factor L, areas scale as L squared. But volumes scale as L cubed. This difference between squared and cubed is absolutely fundamental. Look at this visualization. When we double the linear dimension of a square, its area increases by a factor of 4, not 2. Let's apply this to a classic question. Why can't giants exist? This is a perfect example of scaling laws in biology. The strength of muscles scales with their cross-sectional area. If you double all dimensions of a creature, muscle strength increases by a factor of 4. But body weight scales with volume, which increases by a factor of 8 when you double dimensions. Strength is proportional to L squared. Weight is proportional to L cubed. The ratio of strength to weight is proportional to 1 over L. This means larger animals are relatively weaker compared to their weight. Let's do a back-of-envelope calculation. Imagine scaling a human up to 10 meters tall, about 5 times normal height. Our scale factor L is 5. Weight increases by 5 cubed, which is 125 times. But leg bone and muscle strength only increases by 5 squared, which is 25 times. The stress on the bones is 125 divided by 25, which is 5 times higher. The giant's legs would likely collapse under their own weight. This is why elephants have proportionally much thicker legs than mice. They need extra structural support to handle the increased stress from the square-cube law. Now let's explore scaling laws in mechanical engineering and materials science. Here's an interesting question. Why are small structures like paper clips or needles relatively much stronger than large structures like bridges? Consider a horizontal beam supported at both ends. The stress in the beam due to its own weight depends on scaling. The weight is density times volume, proportional to L cubed. The cross-sectional area that supports this weight is proportional to L squared. Stress equals force divided by area, which is proportional to L cubed over L squared, which equals L. So stress increases linearly with size. This means larger structures experience proportionally more internal stress from their own weight. A steel needle can support itself easily, but a steel bridge of the same proportions would collapse. One of the most fascinating scaling laws in biology is Kleiber's law, which relates metabolic rate to body mass. Kleiber's law states that metabolic rate is proportional to mass to the 3/4 power. This is not what you'd naively expect. You might expect metabolic rate to scale linearly with mass, but it doesn't. Why 3/4? Heat production from metabolism scales with volume, which is proportional to mass. But heat dissipation happens through the surface, which scales as mass to the 2/3 power. Surface area is proportional to m to the 2/3 power. The 3/4 power emerges as a compromise between these competing effects and the fractal-like structure of circulatory systems. A mouse has a much higher metabolic rate per kilogram than an elephant. The mouse must eat proportionally more food relative to its body weight to maintain its body temperature. Let's shift to electronics and semiconductor physics, where scaling laws have driven decades of technological progress. Moore's law observed that transistor density on chips doubles approximately every 2 years. This is a scaling phenomenon. As transistors get smaller, several beneficial things happen, according to Dennard scaling. Switching speed increases inversely with feature size L. Smaller transistors switch faster. Power consumption per transistor scales as L squared, decreasing dramatically with miniaturization. Transistor density scales as 1 over L squared. When you have the feature size, you can fit 4 times as many transistors in the same area. However, scaling has fundamental limits that we're now encountering. Below about 5 nanometers, quantum mechanical effects like tunneling become significant. Electrons can tunnel through barriers that should be insulating. Even though power per transistor decreases, packing billions of transistors creates enormous heat density challenges. At the nanoscale, surface effects dominate over bulk properties. This leads to entirely new physics and chemistry. The number of surface atoms scales as L squared. The number of bulk atoms scales as L cubed. The ratio of surface to bulk atoms is proportional to 1 over L. For a 10 nanometer particle, a significant fraction of atoms are on the surface. Consider gold nanoparticles. Bulk gold is chemically inert and has a characteristic yellow color. But 10 nanometer gold particles appear red due to surface plasmon resonance. And they become catalytically active, unlike bulk gold, because so many atoms are exposed on the surface. Let's calculate what fraction of atoms are on the surface of a 5 nanometer spherical particle. The particle radius is 5 nanometers. A typical atomic radius is about 0.15 nanometers. The surface layer is about 1 atomic diameter thick, approximately 0.3 nanometers. The volume of the surface shell is approximately 90 cubic nanometers. The total volume is approximately 524 cubic nanometers. About 17% of the atoms are on the surface. This is a huge fraction compared to bulk materials. In chemistry, scaling affects reaction rates dramatically, especially for heterogeneous catalysis. For reactions occurring on surfaces, like catalytic converters, the reaction rate depends on available surface area. Reaction rate is proportional to surface area, which scales as L squared, but the amount of material scales as L cubed. This is why catalysts are made from nanoparticles rather than bulk material. You get much more surface area per unit mass. Same mass of gold. Bulk form has minimal surface area, but divided into nanoparticles, the total surface area increases dramatically. In fluid mechanics, the Reynolds number determines whether flow is laminar or turbulent, and it's fundamentally a scaling parameter. The Reynolds number equals density times velocity times characteristic length divided by viscosity. At low Reynolds numbers, typically less than 2000, viscous forces dominate and flow is smooth and laminar. At high Reynolds numbers, inertial forces dominate and flow becomes turbulent and chaotic. This has profound implications for locomotion at different scales. Consider swimming. For bacteria swimming in water, the Reynolds number is about 10 to the minus 5. At this scale, water feels like thick honey. For humans swimming, the Reynolds number is about 10 to the 6. Water feels relatively thin and you can coast using inertia. A bacterium cannot coast. The moment it stops moving its flagellum, viscous forces bring it to an immediate halt. It's like trying to swim in molasses. Here's another scaling question. Why can small insects survive falls from any height? A mouse can survive falling from a tall building, but a horse would be killed. The answer lies in terminal velocity and how it scales with size. Gravitational force pulling the insect down is proportional to its mass, which scales as L cubed. Air resistance, which opposes the fall, is proportional to cross-sectional area, which scales as L squared. Terminal velocity is proportional to the square root of L. Smaller creatures have much lower terminal velocities. The impact force when hitting the ground depends on kinetic energy, which depends on mass times velocity squared. Kinetic energy at impact scales as L to the 4th power. Impact stress on the body, which is kinetic energy divided by cross-sectional area, scales as L squared. Smaller animals experience much lower impact stress. This is why an ant can be dropped from any height and walk away unharmed, but this doesn't work for humans. Let's examine how cooling rates scale with size, which has implications from cooking to industrial processes. The total heat capacity of an object scales with its volume. Heat capacity is proportional to L cubed, but heat loss to the environment occurs through the surface. Heat loss rate is proportional to L squared. The characteristic cooling time is proportional to L. Larger objects cool more slowly. This explains why small, warm-blooded animals like shrews need proportionally more insulation and must eat constantly. They lose heat much faster relative to their body heat content. This also explains why a small potato might take 30 minutes to bake, but a large turkey takes several hours. cooking time scales roughly with the linear dimension. In optics and imaging, scaling laws impose fundamental limits on resolution. The diffraction-limited angular resolution is approximately wavelength divided by aperture diameter d. Larger telescopes and microscopes have better resolution because the aperture d appears in the denominator. However, you cannot indefinitely improve resolution by simply scaling up, because the wavelength of light sets an absolute limit. The best possible resolution is approximately half the wavelength. For visible light around 500 nanometers, this limits resolution to about 250 nanometers. This is why electron microscopes use electron waves, which have much shorter wavelengths than visible light, enabling nanometer scale resolution. Let's consider how gravity and planetary properties scale with size. Here's an interesting question. Why are small asteroids like tumbling potatoes, but large planets are nearly perfect spheres? The gravitational pressure at the center of a body is proportional to density squared times radius squared. But the material strength that resists deformation is a property of the material and doesn't depend on size. For small bodies, material strength exceeds gravitational pressure, so they can maintain irregular shapes. For large bodies, gravitational pressure exceeds material strength, forcing the body into a sphere, the shape that minimizes gravitational potential energy. For rocky bodies, the critical size where this transition occurs is around 500 kilometers in diameter. Many biological systems follow allometric scaling laws, which are empirical power law relationships. Allometric scaling follows the form y equals a times m to the power b, where y is some property, m is body mass, and b is the scaling exponent. Many biological properties follow these power laws with characteristic exponents. Lifespan scales as mass to the 0.25 power. Larger animals tend to live longer. Heart rate scales as mass to the negative 0.25 power. Larger animals have slower heart rates. Breathing rate also scales as mass to the negative 0.25 power. Here's a remarkable fact. If you multiply lifespan by heart rate, you find that most mammals experience roughly the same total number of heartbeats in their lifetime, about 1 billion. It's crucial to understand that scaling laws have limits. You cannot extrapolate them indefinitely. At extreme scales, material properties themselves change. Steel behaves differently at the atomic scale than in bulk. New physical phenomena emerge. Quantum mechanics dominates at small scales. Relativistic effects matter at high speeds. Geometric constraints impose limits. You cannot pack neurons more densely than atomic spacing allows. Thermodynamic limits become important. Heat dissipation limits how fast computers can operate. Understanding scaling laws is essential for practical engineering across many domains. In aerospace, large aircraft are more fuel efficient per passenger because drag scales roughly as L squared, but passenger capacity scales as L cubed. In civil engineering, tall buildings need disproportionately strong foundations because wind loading and seismic stresses scale unfavorably. In medicine, drug dosing scales approximately with body weight because metabolic processing scales with volume, not surface area. In microfluidics, mixing fluids is extremely difficult because low Reynolds numbers mean flow is laminar with no turbulent mixing. Let me summarize the universal principles we've covered. The square-cube law is foundational. Areas scale as L squared, while volumes scale as L cubed. The surface-to-volume ratio decreases with increasing size, profoundly affecting heat transfer, chemical reactions, and structural strength. Power laws with different exponents describe how various properties scale, from metabolic rate to electronic switching speed. Dimensional analysis is a powerful tool for predicting how systems will scale without detailed calculations. Scaling laws have limits and eventually break down when new physics emerges or material properties change. Understanding scaling is essential for rational design across all scales, from nanotechnology to megastructures. Scaling laws reveal deep connections between seemingly unrelated phenomena across different scientific disciplines. They explain why nature looks the way it does, from the shape of cells to the structure of galaxies. They set fundamental limits on what is physically possible at different scales. And they guide engineering design and optimization by revealing how performance metrics change with size. Mastering scaling laws provides powerful intuition that applies across all of science and engineering, allowing you to make quick estimates and predictions about systems you've never encountered before.